zip through this stuff and get you out of here. All right, so 6.3, exponential functions is what we're going to start with. Exponential functions look like this. They have f of x equals c and then a to the x. This c is what we call the initial value. And then the a, that's the base right there to that exponent of an x, is either the growth or the decay factor. Okay, growth or decay factor. And so what we're going to do is we'll look at some ordered pair sets and decide if it's exponential growth or exponential decay, and then try to write the equation for that in this form. It'd be the first thing that we do, and then we'll get into some fun stuff of solving some exponential functions or exponential equations, and then we'll do some stuff with some logarithms and things later today. So good stuff. All right, so question that we'll be answering is the set of ordered pairs exponential? And when we look at exponential, we got to think about what does it mean to be exponential growth or exponential decay. Exponential growth, when you think about it as just a sketch of a graph, you're talking about taking numbers that start out pretty small, but then they grow really fast. So when things grow exponentially, they grow extremely fast. Good common example of that would be like bacteria, germs. You talk about the flu epidemic, during the flu season. The reason is because that virus grows very fast, and exponential growth with that, so it really spreads quickly. And then exponential decay is just the opposite. You start with really large numbers, and then you drop to small numbers very, very quickly. So that would be exponential decay. And don't see that as much in just everyday things, but if you think about carbon dating, if you study that or anything, carbon dating is done using exponential decay of the carbon atoms in whatever object you're trying to date out of that. So there's a use for exponential decay. Exponential growth is also used for savings accounts. If you're investing into a savings account or an IRA or some sort of invest type account that's not like a sell and trade stock market account, but it's a steady percentage. It's an exponential growth because you're always putting the interest back into the account.
The bigger the base, the faster.
Right, exactly. So as your base gets bigger, your growth goes up much faster and all that. So there'll be some application of that stuff toward the end of this chapter. So we'll get into that. All right. So what we're going to do is look at a set of ordered pairs and then decide, is it exponential or not? So let's just start with this one. 0, 5, 110, 220, 340, 480. So just 5 ordered pairs there out of that. And if this were linear, it would have a slope that's the same. And remember, finding slope, was the y2 minus y1 over x2 minus x1. And if we tried that with this problem and we just took 2 ordered pairs, 10 minus 5 over 1 minus 0, we'd get a slope of 5 for that ordered pair set. But if we did a different ordered pair set, we don't get the same number. So we know it's not linear. So the way to decide if something is exponential is to look at what's called the common ratio. And the common ratio is exactly the same thing as the growth or decay rate. Oh, we said factor earlier, so we'll just call it factor. Okay, common ratio and the growth and decay factor, same thing. Okay, so what we want to do is take the ratios. So we're going to take 10 over 5, and that ratio is 2. And then we take the next two y values, 20 over 10, and it has ratio of 2. If I take 40 over 20, it has ratio of 2. 80 over 40 has a ratio of 2. That one's a perfect example of a exponential growth because it does have exactly the same ratio. As x increases by the same amount, the y doubles in this case every single time. Won't always be perfect like that, but when we're dealing with these, we're just trying to get the idea of what exponential growth does. So what this does is it tells us that the c value, or the common ratio, is equal to 2 in that function c a to the x. Okay, so we know that 2 is going to go in the place of the a. Excuse me, not c. C, this is a. So we're going to put 2 in the place of that a. So f of x is equal to c and then 2 to the x power. And then what we've got to do is find out what's the initial value. And if the ordered pair is in there, it's really easy to see that when x is 0, then I could find that really, really easy. And that f of 0, we plug a 0 in for x, but what do we know that y is when x is 0? It's 5. So c, and then 2 to the 0 power is 1, and we divide by 1. So 5 is equal to c. So that means our function for this particular set of ordered pairs is 5 times 2 to the x. And we can verify that using our graphing calculator. We go to y equals and type in 5 times 2. And you get the raised to the x, you put the caret symbol, which is right below clear. And then just put the x as your exponent. And then hit graph. And I'm going to hit zoom 6 so that I get a normal looking thing there. And I can hit trace. And if I type in those x values, 0, I see I get the y value of a 5. If I type in a 1, I get the y value of 10. If I type in a 2, I get the y value of 20. All that. So I'm checking those x values. You can see that I get the same y value that my table had in it. So I can see that fits my table really well. Okay. Let's look at another one. Example B. Let's say we had x values of -1, 0, 1, 2, and 3. And then the y values are 32, 16, 8, 4, and 2. We can see that as x increases, what happens to the y values? It looks like they're dividing by 2. So if we look at the common ratio, the way we're going to do that common ratio is going to be 16 over 32, which would be 1/2, and then 8 over 16, still 1/2. 4 over 8, still 1/2, and 2 over 4, still 1/2. So we know that for our function, the a value is 1/2. And then we can use any of the ordered pairs we want to find out what c is. If I used f of 1, if I use this ordered pair, I would have 8 is equal to c times 1/2 to the first power, and c times 1/2 for 8, and then I multiply by 2 to get rid of the 1/2, and 16 equals c, which makes sense because I saw the ordered pair where 0, 16 was there. If I've got that ordered pair, kind of the shortcut is that's c, that 16 would be c, but you can use any ordered pair to build your equation. So 16 times 1/2 to the x. I always just put my fractions in parentheses there. And again, you could graph that. We know that this is going to be 16 times. I'm going to do 0.5 raised to the x. Easier to type in. Notice how that one is, the red one is the one we're doing right now, example B. It's exponential decay because it's going down as you move to the right. The first one was exponential growth. So if the A value is a big number, like improper fraction or a larger whole number, then you're dealing with exponential growth. If it's a small fraction, so just a regular fraction like 1/2, 2/3, anything less than 1, then it's going to be exponential decay. That's always the case there. So, but easy to do. We'll incorporate a little bit with the graphs and talk about transformations and translations like we did back in chapter 3 is where we started all this mess with the transformations and translations, and we've kind of kept it going for 4 chapters now of stuff. So if you had an example, f of x is equal to 2 to the x plus 4, what does adding something on the outside do to the graph? Of shifts it not to the right, because it's on the outside, it would shift it up.
Oh, yeah, you're right.
Up 4 units. If it were f of x equals 2 to the x minus 4, like that, that would be moving it to the right 4 units because it's in with the x, inside out of that. F of x is equal to 2 to the negative x minus 5. Simple like that. The minus 5 on the outside does what? Down 5. Down 5 units. What does the negative on the inside of it do? Flip across what? Flip across. And remember, on the inside is going to be a horizontal movement, so it's going to move it left to right. Remember, the things that happen to the x move it left or right. So a negative on the x there would reflected across the y-axis. Those are a little confusing because the we say y reflect across the y-axis, but that's actually a horizontal movement, even though the y-axis goes up and down. So that's if the negative were like out here in the front, that would be across the x-axis. That's how that would differ. With the negative out in the front, outside off of the x, would be across the x-axis. All right. So those are the kind of abstract things in this section. The next thing in this section is solving some exponential equations using just basic math kind of stuff. So we're not going to use anything fancy like a logarithm or anything to solve these. So we're going to solve exponential equations. And how this kind of works is what you're trying to do is create an equation where the bases are the same. So if we had a base of a 2 on the left side, the side that has the variable, we want the right side to have that same base. So we want it to look like this, like 2 to the 8th power. And what that allows you to do is if 2 to this exponent is equal to 2 to the 8th as an exponent, then those two things have got to be equal to one another. So we just then, if we can get the bases the same, we can set up a quite easy equation there, x plus 5 equals 8, and solve that and get x equals 3. Where it gets a little bit more difficult is when they don't give it to you in that way already. So what you've got to think about here is not necessarily common factors, but common bases. So you got to think about, okay, the left-hand side has a 2 as the base, and 2 is prime. I can't do anything to it. So I'm going to stick with that as my base. How can I rewrite 16 with 2 as a base? It would be, well, let's think about 16. It's 4 times 4, 2 times 2, 2 times 2. 16 is actually 2 to what power? 2 to the 4th. So we have 2 to the x plus 1 is equal to 2 to the 4th. And that allows us to say, oh, well, then the equation is just going to be x plus 1 is equal to 4 and solve that. X would be equal to 3. All right, so if we can get the bases the same, then the equations are super easy. Let's try this one. 3 to the 5x is equal to 81. Change the base a little bit here. So what do we know about 3? It's prime. So I know I can't do anything to that side. So I got to think, okay, how can I rewrite 81 as a bunch of 3s? So if I think about 81, I think, okay, that's 9 times 9. That's how I think about getting 81. And then that's 3 and 3 and 3 and 3. So 81 is actually 3 to the 4th power. So we have 3 to the 5x is equal to 3 to the 4th. Since the bases are the same, then that 5x and that 4 are my equation. So 5x is equal to 4. And then divide by 5. And we get a fraction as an answer, and that's quite okay. That happens. So if that base that the variable is on as the exponent is prime, then you know you got to try to get that other side to be that same base out of that. Where it gets a little bit more difficult is when you have something like this. 4 to the 2x minus 1 equals 8 to the x. So this one's a little bit of a double whammy because it's got an x on both sides, and we know 4 and 8 are not, neither one of them are prime. So we've got to think about, okay, how can I rewrite 4 and how can I rewrite 8 so that they're the same base? So the most common misconception here or mistake that folks make is they say, oh, well, 4 goes into 8, but it doesn't go into it 4 times. It only goes into it twice. So that doesn't allow you to rewrite it as an exponent. That allows you to rewrite it as a product. So we're looking to try to rewrite this some other way. So when I look at that, I look at the 4 and say, okay, it's not prime. So I'm not even going to think about the 8 until I get the 4 fixed to be a prime number. So I'm going to break down the 4. It's 2 and 2. So it's 2 squared to the 2x minus 1. And then now on the left-hand side, I've got a base that's a prime number. And then I want to think, oh, how can I rewrite 8 with a base of a 2? And it would be 2 to the 3rd power. 2 times 2 is 4 times another 2 is 8. And now I can set up my equations using exponent rules. I know that what happens between this 2 and that 2x minus 1. What's the rule when there's exponent outside of the parentheses? What do you do with those exponents? If there's an exponent outside the parentheses, you multiply. So we're going to multiply 2 times 2x minus 1. So this is that 2 that's right there. And then this 2x minus 1 is that. And then on the other side, the same thing happens. We got 3 times x, so that's 3x out of that. And then we've got a nice, easy, 7th grade algebra problem here. We just get x by itself. So we're going to distribute 2, that's 4x minus 2 equals 3x, and then subtract 4x. Negative 2 is equal to negative 1x. And this works out real nice because negative 1 goes into negative 2 2 whole times. X is 2. So if the base isn't prime, then you need to look at trying to get it to be prime so that you can know what to do with the other side. Let's do another one there. 9 to the 2x is equal to 1 over 27. Number 9 to the 2x power is equal to 1 over 27. So this one looks super hard because you got a fraction thrown in there, but the first thing that you want to look at is look at the base on the side the variable's on, okay? And it's only on the left side here, so the base is a 9, but I know 9's not prime. So I know 9 breaks down into 3 and 3, so that's really 3 squared. And then on the other side, that gives me the clue that, hey, I need to figure out how to rewrite 1 over 27 as a 3 with an exponent, okay? So I think about when I've got a fraction, especially one that has a 1 on the top, I always just start with the bottom number and say, okay, 27. Let's break that thing down. That's 9 and 3, 3 and 3. So that's really 3 to the third power is what 27 is. So this is really 1 over 3 to the third power. How can I rewrite that where it's not a fraction using exponent rules? How can I take this 3 to the third and move it up to the top? Remember, there's a negative exponent rule that if you've got a negative exponent, that you can rewrite it and change the sign of it by moving its location. So if it's in the numerator and it's negative, if you move it to the denominator, it becomes positive. And the opposite is true. If it's negative in the denominator and you move it up to the numerator, it becomes positive. So here, if it's positive in the denominator, but we don't want it in a fraction, we want to rewrite it to where it's not a fraction, I can move it up to the numerator and get 3 to the negative third. Is the same thing as 1 over 27. Okay, and you can check that with your calculator if you need to. 3 raised to the negative 3, and then hit math, enter, and it'll crank back that fraction at that way. Anytime you see a fraction, you got to think negative exponent's going to happen here. That's kind of the clue that you want to use to help you know, I got to have a negative exponent if it's a fraction on the side that doesn't have the x. Okay, so now that lets us set up our equations. So we've got 2 times 2x is 4x equals negative 3. Real easy math there. One stepper. So getting a fraction based with a base, you got to think negative exponent. Let's do another one of those because that's a tough concept there. Let's see. Let's try this. 8 to the 5x is equal to 1 over 64. Yeah, let's not do 64 because 64 and 8 have too much in common. Let's do 128. That's better. All right. So when I look at that, I see the 8 there, and I know, hey, 8's not a prime number. So I'm gonna work with that side first so that it gives me some clues about what to do on the other side. So I know 8 is 4 and 2, 2 and 2. So it's 2 to the third power. That's what I know 8 is. And the more of these you do, the more you'll just skip that factor tree step, and you'll 8 is pretty common. I know it's 2 to the third. Now, what I've got to think about here with the 128 is breaking it down. And so I'm thinking of getting 2 as the base. So I'm going to start breaking it down with 2. So that'd be 64. And break 64 down with a 2. That'd be 32. Break 32 down with the 2. 16, 2, 8, 2, 4, 2, 2. So 1, 2, 3, 4, 5, 6, 7 twos. 1, 2, 3, 4, 5, 6, 7. Yeah, 7 twos. So that is 1 over 2 to the 7th. And if I want to rewrite that where it's not a fraction anymore, it'll be 2 to the negative 7. And then from there, we set up our equation. 3 times 5x is 15x equals negative 7. So the bases just drop off. And then get x by itself. Right, or divide by 15. Get a fraction in this case, negative 7 over 15. And because it's an equation, you can always take that answer and plug it back in for x in the original problem and see if it equals the same thing on the other side. So if I did 8 raised to the 5 times negative 7 over 15, that, and then hit math, enter, 1 over 128. So I can always check. Because it's an equation, I can always plug back in and check. So that's always a plus side to doing equations, is that you can plug back in and check. All right. Let's look at one that is slightly different. 4 to the 3x squared is equal to 8 to the x. So with this one, we've got bases of 4 and 8, which neither of are prime. And we've kind of already done one that had these same two bases. So we need to change them into a base of what? 2, yeah, because that's the prime number that goes into both of those. We know 4 is 2 squared. That's 3x squared there. And then we know 8 is 2 to the 3rd power. And then once we've done that, we know, hey, I've got exponents. I multiply them together. So that's going to give me 6x squared is equal to 3x. So I'm just taking the exponents and multiplying them together and setting those equal to each other, dropping the 2's off. Now, this is where we got to remember, okay, that's a quadratic equation. What do I have to get it equal to in order to solve it? And in order to solve it using any of the methods that we know how, I've got to get it equal to 0 before I can do anything. Anytime you got an x squared in your problem, get it equal to 0 first, and then go from there to solve it. So once we get it equal to 0, that opens up all of the rules that we learned about solving quadratics, which was you could factor it, you could use quadratic formula, that x equals negative b plus or minus square root of b squared minus 4ac over 2a. That's legal now because it's equal to 0. It's quadratic. This one, the easiest method to solve on this one, because it's so short, is a factor. GCF of that would be 3x. So that'd leave you 2x minus 1. And then you set each factor equal to 0. So we're going to get 2 answers on this one. X equals 0. And then this one, you add 1 and divide by 2. And x equals 1/2. And then I would need to check both of those in my original problem to make sure that they work. If I plug in a 0, I get 4 to the 0 power equals 8 to the 0 power, which anything to the 0 power is always what? 1. It's always 1. So that one, 0 works. And if I plug the 1/2 in there, I'm going to get 4 to the 3 times 4 raised to the 3 times 0.5 squared. I get that answer. On the other side, I've got 8 raised to the 0.5. Exact same decimal there, so it checks in both of those answers work. It is possible that if you get more than one answer, that one of them doesn't work and the other one does. You need to check them, especially when there's more than one answer, just to make sure that they both work. Yeah, it's possible that one doesn't work and one does work, but that really comes more into play when we start throwing the logarithms in there. But if you'll get in the habit of checking them now, you won't even have to think about it when we get to other stuff. All right. So looking at that base, it's getting the bases the same, like we did at this step along the way is the key. And sometimes they throw in this exponential number, and so we'll talk about a little bit about it. E is called the exponential number. It's kind of like pi. It was a number that was used enough that they decided, hey, instead of writing out that number every time, then it's better. We're better off just putting an abbreviation for it, and then we're going to call it E. E to the first power is about 2.71, and then it keeps going. There's a lot of decimals after that, so it's a lot like pi in that it never terminates and never ends. It just has a big long decimal. It's used a lot in the life sciences when you talk about half-life of cells or bacteria, or growth of cells or growth of bacteria. E is used in the formulas for calculating when the population of that particular cell group or bacteria group will reach a certain level. So it's used in there in a lot of the natural sciences. You'll see that. So we're going to work a little bit with some equations that have E as the base, and they're actually, to me, a lot easier than the others because you don't have to really do much to make the base the same. The base is E, and it's E, and you don't have to do anything to make it E. So to me, they're easier. But we'll kind of start introducing it in this section. M. So e to the 2x is equal to e to the x minus 5. So you see that you have the bases that are already the same. So it's a very easy solve here. You just set up the equation and solve it. So subtract x. So that'd be x is equal to negative 5. And that's your answer. And we could plug it back in and check it if you wanted to. To get E with the calculator, if you're going to plug back in and check, which I advise that you do, to get E with the calculator, you have to hit second. And then down here on the left side, right beside the number 4, is this LN button. In blue there beside it, it says E to the X. So that's where you get E to a power. So I would hit E 2 times negative 5. That's the left-hand side of my equation. I get this ugly decimal here, which is what you would expect from a decimal number being raised to a power. And then on the other side, I'm going to do E to the negative 5 minus 5, which is the exact same ugly decimal number. So we know that that's the correct answer for this particular equation. So they can't all be that easy. So we got to step it up a little bit here and make it a little tougher on you, but not too bad. This is really not bad at all. So this equation has e to the 7x times e to the x squared is equal to e to the negative 12. So this is a really weird looking equation because it's got all this e stuff and it's got a multiplication symbol in between them. Okay, so this is where we've got to remember some exponent rules about what do you do with exponents when the bases are the same and you're multiplying. You add them. That's right. So this is really, this whole side here could be rewritten as e to the 7x plus x squared. Right?
But E not be squared.
E is not going to be squared because you're just adding these two exponents. So the base never changes on that because it's kind of, if you multiply x times x, that's x to the first times x to the first. 1 plus 1 is 2. That's how the squared happens, is you're adding the exponents. So here, because those exponents are stuff with variables, we're just adding them together out of that. All right. And now the bases are the same. They're both e on both sides. So once you get those the same, then you're going to set up an equation. And I'm going to rearrange it into descending order there with x squared coming first. And then because it has an x squared in it, what do I need to get it equal to? 0. So I need to get it equal to 0 before I do anything. So I'm going to add 12. And it's not like any of those, so it's going to be x squared plus 7x plus 12 equals 0. And that opens up all of the things with quadratics, either factoring by x method or quadratic formula would work well with this one. Both of those methods work well with this one. I like to factor. It's a little faster on this problem because it does factor. Multiply to be 12 and add to be 7, 4 and 3, right? So that would give us the factors x plus 4, x plus 3, and I'd set each of those equal to 0. And we get our answers from there. X equals -4, x equals -3. And then I could go back to my original problem and check both of those in the original problem, and I'll go ahead and tell you that they both check for this problem. They both work as well. Again, most of the time, unless you're involving a logarithm in solving, your answers are all going to work. But if you'll get in the habit of checking them now, it'll save you the trouble of not checking them later, because the logarithms really change it up a little bit. And if you don't check, you end up getting some extra answers that you don't really work. So get in the habit of checking them now. All right. Yeah, absolutely. If you wanted to do it that way, you could do x equals -7 plus or minus b squared minus 4ac would be 7 squared minus 4 times 1 times 12 divided by 2 times a, so 2 times 1. And you could work that out and get -7 plus or minus be 49 minus 48, which would be 1. So we'd have -7 plus or minus the square root of 1 over 2, which we know the square root of 1 is 1. So we'd split that up into -7 plus 1 over 2, which would be -3, and then -7 minus 1 over 2, which is the -4. We still get the same answers. Well, I don't know. Here's the thing with quadratic formula, it works every time. Factoring won't always work. So that's why I use factoring when I see that it does work, is because it's faster, but it doesn't always work. So sometimes I'll end up spinning my wheels trying to factor something when I could have just done quadratic formula and been done. So there's give and take on all of it. So it just takes a little. It totally does not matter which method you use to solve that. Whichever way works. But understand, factoring doesn't always work. Quadratic formula does. So if you do them all with quadratic formula, you're good. It's going to work. But factoring won't always work. All right. Okay, so that's section 3 for chapter 6. Let's dive into section 4 and see what we can learn about logarithms and logarithmic functions. So section 3 was about exponential functions. Section 4 is going to be about logarithmic functions, and then section 5 we'll talk about the properties of logs. So what you need to keep in mind is logarithms are logarithmic functions. Logarithmic functions are the inverses of an exponential function. All right. Another thing, and I had a teacher tell me this one time, and at the time it didn't make sense. But when we get into section 5, and talk about the properties, it really starts making some sense, and it helps you remember the properties really, really well. If you'll remember, a logarithm is an exponent. It will help in learning some of these rules that we're going to talk about and rewriting logarithms as exponential functions and rewriting exponential functions as logarithms. Sometimes a function is easier or more easily solved or more easily understood if it's in exponential form. Sometimes it's more easily solved or more easily understood if it's in logarithmic form. So we can bounce back and forth between those two different forms using just some basic swaps that happen with logarithms. So I want to show you how to do that. So we're going to start with rewriting the log function. We just, instead of writing out logarithm all the time, log function as an exponential function. Okay, rewrite the log function as an exponential. All right, so we'll start with the first one. First example is just like a basic logarithmic function. And here's how you read that. You read that y equals log base 3 of x. That's how that's read. Log base 3 of x. So this little number here is the base. So when we talk about exponentials, when we were talking about those, we had bases on exponentials, right? So that's the same base. It means the same thing. So when we go to rewrite this as an exponential, the way that works is the base of the exponential. And the logarithm is an exponent. That means it equals the exponent. So whatever the logarithm is equal to, in this case, it's equal to y, that becomes the exponent on the exponential. So 3 to the y, and then is equal to x. And that's rewriting a logarithm as an exponential. Okay, so the base of the log becomes the base of the exponential. Whatever the logarithm is equal to, in this case it was equal to y, that becomes the new exponent. And then whatever you're taking the log of is what the exponential is equal to. Okay. So example B, let's do another one. Let's say we had log base 2 of x is equal to 3. So that looks like a pretty complicated equation, but we know that, hey, if I can rewrite it as an exponential, then it may not be as complicated. So that's log base 2 of x is equal to 3. So what's the base of the exponential that I rewrite it as? 2. What's the exponent? It's always what it's equal to. Always what it's equal to. So it's 3 and then x. So because we could rewrite it as an exponential, we could then solve that really easily. When it was in logarithmic form, it looked foreign and very difficult to do. But when we rewrite it into exponential form, we realize, hey, it's just a number, and it works out really nicely. So that's one of those cases where if we could rewrite it in a different form, it makes it easier to do. So that's kind of what we're working with here, is because bouncing back and forth between logarithms and exponentials can help us in simplifying what we're trying to solve and make it easier. So log base 5, let's do 1 over 25 is equal to x. Okay. So what's the base? That 5 right there is the base. And then what's the exponent? It's always going to be what it's equal to. So it's equal to x. So it's going to be 5 to the x equals 1 over 25. And now we've taken a logarithmic equation and turned it into an exponential equation that looks like one of them that we did when we were doing section 6.3. So again, I may have said this before in this class. One of the things about mathematicians is you'll notice is that we just try to take things that we don't know how to do and turn them into things that we do know how to do. So it's like just manipulate the thing until you get it into the form that you're used to. So we don't like change. We like to keep things the same. So we're just trying to move things around until it looks like something we know what to do with.
Like how we took down use of vector reading to break things down.
Exactly. That's exactly the same idea. Let's do, these are called common logs. And common logs are ones where they don't write the base. Common logs are ln and then just plain log. Ln of x is equal to y. So natural log is how you normally would read that. Natural log of x is equal to y. Natural log is shorthand for log with a base of an e. It's not really that much shorter, but since e had its own special notation, then the logarithm that's the inverse of that needs its own special notation. So that's why the natural log is used. So natural log, anytime you see it, your brain needs to think, oh, that's log base e. Okay. And so if we rewrite that as an exponential, the base would be e, the exponent would be y, and it's equal to x. So natural log is log base e. And then everything else works the same way as far as rewriting it as an exponential. So you want to think, hey, that's log base e. Those are the same things. Okay. When you have the other common log, which is just log, log of x is equal to 3. When they don't put a base right there, there's an understood base of 10. And the reason it's an understood base of 10 is because we live in a base 10 number system. If you think about the number 264, that's 2 100s, 6 10s, and 4 1s. If I think about those in terms of 10 bases, 100 is 10 squared, isn't it? 10 is 10 to the first, and 1 would be 10 to the 0. So when we think about a number, the number system that we live in is the base 10 number system. If you get into electronics or things like that, it's a base 2 number system because it's either on or off. It's a 1 or a 0. If you get into some computer coding is hexadecimal, which is base 6. And so you think about numbers in terms of 6 sets of 6 instead of sets of 10. We learned since we were in preschool that we're counting. We first thing they taught us to do is count to 10, right? And then after that, the next milestone was being able to count to 100, and then we've gone up from there. Obviously, or hopefully we have anyway. But the understood log, when there's nothing written there, it's an understood log base 10. Okay, so if we go to rewrite that as an exponential, it'd be 10 to the third power is equal to x. What this is going to do is it's going to help us when we go to solve some equations that involve logs, or solve some equations that involve exponentials. If we can rewrite it as a logarithm, it can help us to solve it and maybe do it in a quicker and easier way out of that. So that was going from a logarithm into an exponential. Let's go the other direction. Let's write the exponential as a log. Okay. Let's say we had 3 to the x is equal to 27. What is the base of that equation? No. Remember, what's a base when we're talking about exponents? The base is the number that has the exponent on it. So what has the exponent on it in this equation? The 3. So that's the base. This is our base. So that's going to tell us, hey, you need to use log base 3. And a logarithm is always equal to the, go back up here to the top here. A logarithm is an exponent. Is a way of saying equals. So x is what this thing equals. So that leaves only one place to put the 27, and that's what you're taking the log of. So the base of your exponential becomes the base of your log. What it's equal to is going to be the exponent, like goes down there, and then what the exponential is equal to is what you're taking the log of. Let's say we had, we'll go with something that's not even a number. A to the 4th is equal to 24. Your base is A, so that's going to be log base A of 24 is equal to 4. Good job. Okay, easy stuff there. So we had 5 to the x is equal to 625.
Log of 5.
Log base 5. There you go. Good job. 10 to the x plus 1 is equal to y.
Log 10 of y.
All right. But I don't need to write the 10 there. You're usually not going to see it written there. It technically wouldn't be wrong if you wrote it there, but you normally don't see it there. But that is correct. Good job. All right. Let's do e to the square root of 2 is equal to y.
Log of e, or log e. What am I trying to say? Base e.
That's the right way. Log base e of
y.
Okay. So how do we write log base e?
Oh, it's the natural.
There you go. Alien natural log is how you want to write that. It's even more rare to see. You would almost never see it written that way. This is the correct way. Okay? You're almost never going to see it written that way. But technically it's correct, but it's you're just not going to see it written that way. Now let's put this to work and actually work out some logarithms and evaluate them without a calculator. So this is going to be without a calculator, and we'll do some with a calculator. My students always ask, well, why are we having to do it? We paid $100 for this calculator. Why am I not getting to use it? Nobody said you couldn't use it. I'm just saying it will help you as we build up the rest of chapter 6 if you'll try to do some of this without the calculator. Not saying you can't check it with the calculator. I absolutely would encourage you to do that, especially for quizzes and tests. But if you'll make your brain kind of work at this a little bit, it'll speed you up when we go to do the other stuff later on with logarithmic equations and things like that. So let's just evaluate this without a calculator. So evaluate is the real instruction, but we're going to do it without a calculator. So let's do log base 2 of 16. Okay. Now, nobody memorizes log base 2s of numbers because they're going to be, there's a lot of them, and it'd be borderline impossible for most of us to memorize those. So what you want to look about at this is to think about it and create yourself a little equation that you can turn into an exponential, because our brain doesn't think too well in logarithms, but it thinks pretty well in exponential stuff because we learned multiplication tables growing up. So if we can turn this into a multiplication problem, we can turn it into something we know how to do. So the idea is, again, manipulating the problem to make it something we know about. So I'm going to just make this equal x. So the original problem did not have the equal x. I'm just putting it in there because it's going to help me to rewrite this logarithmic statement as an exponential statement. So how can I rewrite that as an exponential?
So when it equals goes to the x on it.
Yeah. 2 to the x is equal to 16. And now I have an equation like we did in section 3. I've created a problem that I know how to solve. And when I did this in section 3, what was my goal? It was to get what the same on both sides? The base. So I need a base 2 because 2 is prime, right? So 16, if I break that down, is 2 to the 4th power. And the bases are now the same. I don't have to do anything with those now. I just say x is equal to 4. And I've created myself an easy problem to solve because I could rewrite that logarithm as an exponential. Let's say we had this one, log base 4 of 1 over 64. So one with a fraction in there always makes us nervous and makes us, kind of second guess our choices in life. Now, so what I'm going to do is I'm going to introduce a variable to the problem and just set the thing equal to it. I'm just going to say this equals x. And then I'm just going to rewrite it as an exponential. So that's going to be 4 to the x equals 1 over 64. And I know 4 is not prime, so I can rewrite 4 as 2 squared, because I've done that a lot today. And then I'm going to think about 64, and how can I rewrite 64 using 2's? So I know that's 8 times 8, 4 times 2, 2, 2, 4, 2, 2, 2. 1, 2, 3, 4, 5, 6. Is that right? So that'd be 1 over 2 to the 6th power. But that still doesn't have it's got the right base, but it's not written like I need it to be able to set up my equation. So what does the right side turn into? There you go. Good job. 2 to the negative 6. And that'll be 2 to the 2x over here. And the 2's that are the bases. I don't need you anymore. Divide by 2. X is negative 3. And so we know that the log base 4 of 1 over 64 is really equal to negative 3. Now, with your calculator, you can check that stuff. I'll show you how to do that so that you're not stumbling around in the dark here. So the graphing calculator has a nice function. It's called log base. And to get there, you're going to hit math and then press the up arrow and look for this thing called log base. And when you hit that, it should come up with some empty squares there. Does it?
Yeah.
All right. So in that bottom square, that's going to be the base of your log. So we're looking at log base 4. And then in the square inside the parentheses, you want to put the number you're trying to take that log base of. So 1 over 64. And we just hit enter. And it cranks out what we worked out on our own with that. The same thing could go for the previous example, which was, what was it? Log base 2 of 16. If we do math log base 2 of 16, whoops, 2, press the right arrow key. Now 16 and hit enter. We see that it's 4, which is what we found when we worked out that problem. Okay, your calculator can work out any of those things using that log base functionality out of that. So the log base function, even if it's not a pretty number, if they ask us to do the so with a calculator, So if they said do log base 5 of 18, if I'm doing that with a calculator, I know 5 to a power doesn't make 18. So I know it's going to be something. So I'm going to hit math, go to log base. 5 is the base. 18 is the number I'm taking the log of. Crank that out. 1 point. We'll go 3 decimal places there. So 1.796. With the calculator, you can do any numbers, whether they work out beautifully or not, like the ones we did without a calculator. So it works really well. If for some reason your graphing calculator spazzes out and won't do the log base thing, there's this thing called the change of base formula. The change of base formula allows you to take a logarithm of a different base using common logs. So in our case, if we tried to redo example M using the change of base formula, I can use the log button. So over here on the left-hand side, right beside 7, there's a log button. If I do log of 18, close the parentheses, divided by log of 5, it'll get me the exact same answer as doing that log base stuff. So it's always the base on the bottom. That's the way I remember change of base formula. When I was coming up, we didn't have the graphing calculator, or we had graphing calculators, but they didn't do the log base thing. So you had to have the change of base formula. It's kind of fallen out of grace because we've got better programming nowadays for the graphing calculators. But most any calculator, even your cell phone, has a log button on it. If you're using an iPhone, you got to turn it sideways, and it's got a log button on there for log base 10, and you can use that to do logs of that. You can even use natural log. It doesn't matter which common log you use, it still gets you the same number because the way the properties of logs works. No matter which of the common logs you use, the change of base works. So sometimes it's if I'm in a hurry, I usually don't like to hit the math button and then hunt and find. I know I can do that, and that's the way that I did it growing up. So that's the way I do it a lot of times, just because that's the way I'm used to it. And my brain goes there first because that's the first way I learned it. But the log-based function on your calculator shouldn't spaz out and shouldn't ever quit working. But if it did, or you found yourself working on some math and you didn't have your graphic calculator handy, or the batteries were dead, you can still do logarithms with evaluate them with a regular calculator using log. As long as it's got a log button, which most scientifics, or even like I said, even your cell phone one has that capability. So that is evaluating some logs without the calculator, and then with the calculator. Really easy thing there. So let's get into the function stuff with logarithms. Okay, so we'll call it function stuff. All right, when we talked about functions of logarithms or of any kind of function, we talked about domain and range. All right, domain for most logarithms is going to be from 0 to infinity, and the range is normally from negative infinity to positive infinity. The relationship that a logarithm has with an exponential is that they're inverses of one another, and inverse functions swap domain and range. So the domain of a logarithm is the range of the exponential. And the range of a log is the domain of the exponential. Because that's what inverse functions do, okay? One thing that we have to keep in mind at all times is we can never take a logarithm or a log of a negative number. Or 0. Because it doesn't matter what you do. And you remember, logarithms, again, are the same thing as exponents. No number, anything to the 0 powers is always 1, right? So it doesn't matter what the exponent is, you're never going to get a negative number back. If you start with a positive number, you raise it to an exponent, it stays positive all the time. If you start with a negative number, depending on what the exponent is, it becomes either positive or negative, but it never becomes 0. Okay, so we never can take the log of a negative number or 0. So what that key, and it's starred because that's going to be the key to being able to find the domain for various logarithmic functions out of that, because we can only take the log of things that are greater than or equal, or greater than, not equal to, greater than 0. Okay, so you got to think about greater than 0 when you do that. So if we're going to state the domain and the range, so for some problems, state the domain and range example n, say we had f of x is equal to log base 2 of x plus 3. Okay. So it does not matter what base the log is that you have. It has no bearing over how you find the domain and range. The only thing it changes is how fast the curve happens. The base changes the steepness or the sharpness of the curve. So that base of a 2, it doesn't matter if that's a pumpkin sitting there. It really doesn't have anything to do with how you find the domain of that. So when we go in to find the domain, to find the domain, what we're going to do is we're going to take what we're taking the log of, so this stuff, and we're going to take x plus 3 and set it greater than 0, because that's the only kind of numbers that we can take the log base 2 of, are numbers that are greater than 0. We can never take the log of 0 or a negative number. Okay, so we set that up and we solve it. So x has got to be greater than negative 3. So the domain would be from negative 3 to infinity for this particular one. The range, if we look at the graph of this, equals, clear out this other junk I had, I can actually type in that log base 2. So I can hit math, go to log base, make it a log base 2 of x plus 3. Hit graph, I'll show you what's going on. Now, it disappears right here below that line right there. But what's happening is the resolution of my calculator screen is getting so it's not a Retina display or 5K resolution like Mac has now. It's not that great. So what happened is the resolution got so low it couldn't show me all of those numbers that are happening there. So the range, actually, this graph continues down forever. If I zoomed in way down here, come on, get down there, and then I'm gonna move over here to that area. All right, now let's get below that pretty good ways. All right, so you see there's a gap there. If I zoom into that spot, now we see more of the blue line. It gets because it's moving less and less. What's happening is this graph has it's almost vertical, until it gets up here, and then it does that. It gets almost vertical, but it's still moving to the left just a little bit out of that. Then remember, our domain starts at -3, but it doesn't include -3. So there's this kind of this asymptote that goes down the side there. That you remember with the rational things that we had asymptotes in there. Same thing happens with logarithmic functions. You've got asymptotes that this x value is where it starts. It starts at -3, but not including 3. So what happens is this graph gets closer and closer to that dotted line as it goes, but it just keeps inching closer and closer to it. The calculator can't show you how little it's moving, so it just says, forget it.
Like it should be like a point, something.
Yeah.
So thin that it can't.
Yeah, it gets so thin that it can't show it. That's what's happening. That's exactly what's happening. So our domain is from -3 to infinity. We look at that 6. We see it is going to keep going up forever, and this graph keeps going down forever. So our range is from -infinity to positive infinity. The range should never change. It's always going to be there. Okay. Our domain changes on the logarithmics, but our range should always be from -infinity to positive infinity. Out of that. All right, let's look at a little tougher one. I'm going to do f of x is equal to log base 5, 1 plus x over 1 minus x. Got a rational expression inside of that. We want to find the domain and the range. So to find the domain, I've got to take what we're taking the log of and set it greater than 0. And when you're solving a inequality with a rational function or a rational piece, you got to do some interval checking here. So what we've got to find is where does the denominator equal 0 and where does the numerator equal 0. So the denominator equals 0 at +1. So 1 minus x equals 0. That'd be x equals +1. And then the numerator, x 1 plus x, when does it equal 0? At -1. So we look at the interval then for that on the number line. So you got -1, you got +1. I'll put open circles on those because those are numbers that x can't be those numbers. Because if x were +1, then it would have division by 0. You can't have that. If x were -1, then this on top would be equal to 0. And if the numerator is equal to 0, then the whole fraction is equal to 0. And that just doesn't work. You can't have, remember, you can't take the log of a 0. So that's why we're picking those two numbers. Where's the denominator equal to 0? Where's the numerator equal to 0? Those are the things you got to find when you're doing a rational inequality. Now we need to check these areas. So we need to pick a number that's to the left of -1, pick a number that's between -1 and +1, and then pick a number to the right of 1. So make it easier on yourself and pick some easy numbers. -2, 0, and 2. And plug those in to the inequality to see if it's true or false. So if I plug in -2, the question is that greater than 0 when I work that out? So that's going to be -1. That's going to be +3. Is -1 divided by 3 greater than 0? No. So this area is false. So then I go and I check 0. 1 plus 0 over 1 minus 0. Is that greater than 0? So that would be 1 over 1. Yeah, that's true. So this area is true. So right now we know that the domain is between -1 and +1, but it could just skip the +1, and this area over here could be true as well. So I'm going to go over here. I'm going to check the 1 plus 2 over 1 minus 2. And is that greater than 0? That's what we're checking. So that'd be 3 over -1, which is -3. Is -3 greater than 0? Oh, that's false as well. So the only domain for this one, weird, but the domain would be from -1 to +1. Range negative infinity.
And if it had been true on the two sides, where it's gone from -1 to positive infinity.
Now, if it had been, we would have to skip the 1, so you'd have to have a union 1 to infinity. Then, so you'd have -1 to +1, union 1 to infinity. Yeah, that if it had been true on that side. Okay. All right. So not too bad. Not too bad. Let's see. They really don't get much different than that, much more difficult than that. All right, let's look at some solving equations with this, and we may or may not get to the third section tonight. I'm not sure. I'm not going to overload you. Let's solve. What letter we're on here? Same section here. P. So this one we have a logarithmic equation. Log base 3 of 4x minus 7 is equal to 2. And this is where we really employ that idea of rewriting a logarithmic as an exponential to solve. Makes things a lot easier. We don't have to deal with logarithms if we can get rid of them. So what we want to look at is we look at the base of each side, or a base of the logarithm over here, and we got a base of a 3. Well, if I rewrite this logarithmic statement as an exponential, it'll be the base of 3, an exponent of 2 is equal to 4x minus 7. Base, exponent, and then what it's equal to. Always in that order. And then 3 squared we know is a number. It's 9. And now I've got a nice 7th grade math problem to solve to get x. And if I can solve this problem, I've got my answer to my logarithmic equation. That'd be 16 4x divided by 4. X is equal to 4. Now, here's where it gets the checking. You know, I said earlier, you need to get in the habit of checking in that section, because when we throw in the logarithms, it's very important. What we've got to do now is check that solution to make sure that we're not taking the logarithm of a 0 or a negative number. So if I plug in 4, that's going to be 4 times 4 is 16, minus 7 is positive 9, which is okay to take the log base 3 of. Okay, so when you get an answer, check it back in the original problem that has a log in it, and make sure you're not taking the log of 0 or a negative number. If you are, then throw that answer out. It is an extraneous solution, meaning you found it, but it doesn't work in the original problem. Okay. So we had log base x 64 is equal to 2. This one's a little more straightforward, maybe. Well, x squared is equal to 64. And then how do you solve that? Yeah, take square root of both sides. And if I take a square root, what do I have to put in front of that? Plus or minus. And it's got to be there. So I have two answers. I've got x equals positive 8, x equals negative 8. With this one, those are the bases of my log. There are no rules about the bases of the log, only what we're taking the log of. So it's actually okay to have a negative on that one, because it's the base of a negative 8, not a base of a base of an 8 or a base of a negative 8 is okay. It's not taking the log of a negative 8. It's a base. So bases are okay to be negative. Okay. Let's say we had log base 3 of 3 to the 6x is equal to 42. So this one has you can do it the long way, which is to say, okay, well, I'm just going to rewrite it 3 to the 42 is equal to 3 to the 6x. And then That's not bad, because now it's an exponential problem, right? And what happens to the 3's that are the bases? You ignore them, and you just get 42 is equal to 6x. And that's 5 by 6. And 7 is equal to x. And that works out great. I say that's the long way. It was 2 steps, and that's the long way. The short way is to, anytime you have a log base and then a base here that are the same, they just cancel each other out. And you go straight to that equation there. That if you have the log base and the base of your what you're taking the log of are the same. So example would be like log base 5 of 5 to the 3x is equal to 18. Instead of doing 5 to the 18th power equals 5 to the 3x power, you can just go, hey, these things cancel each other out. It's 3x equals 18 and x equals 6. I don't know how much shorter that is. It really doesn't shorten it up much, but it's a property of a log that can kind of give you a head start on some things there. So if the base is the same here and here, they cancel each other out, is what happens there. All right. Let's say we had one like this. 81 to the x is equal to 27. All right. So this one doesn't have a log in it. It's an exponential. So how did we do the exponential ones? Right. Try to get them down to the prime base. So what do we know about the relationship between a prime number that goes into 81 and a prime number that goes into 27? Yeah, that's right. 3 is the smallest prime number that goes into both of those. And if we start breaking down the 81, that's we could do 9 and 9, 3, 3, 3, 3 for that 9. So that's 3 to the 4th power to the x. And then this 27 would be 3 to the 3rd power. So we end up with 3 to the 4x is equal to 3 to the 3rd. And what we did in the previous section is we just ignored the bases and said, oh, they're going away. It's going to should be 4x equals 3. But mathematically, we were kind of doing a hand waving thing and saying, okay, we'll just ignore the bases. There's actually some math that goes in with getting rid of those bases. The way to get rid of those bases is to take the log of the same base. So if I take the log base 3 of both sides, they cancel each other out using that property that we talked about just a minute ago. Okay. So that's really what's happening to let us ignore the bases. That we really do just have the equation 4x equals 3 and x equals 3/4. We really do have that. It's the same process, but taking the logs in it, what that does is it opens up the idea that what if you had 3 to the 5x is equal to 24? What do we know about 24? Is there any way to write 24 as a base of a 3? Because if I think about breaking down 24, I think, okay, that's 12 times 2, and then that's 6 times 2, and that's 3 times 2, and it doesn't work out to be the same number as a base. It's not a nice exponential number, so it doesn't work well for that. So I can't use that trick here. So I've got to have some other way. The other way is to think about it and say, okay, well, this has a base 3. So in order to get rid of that base 3 and get the 5x out of the exponent, I've got to take the log base 3 of each side. And what happens is the log base 3 cancels out that base of a 3. And I get 5x is equal to log base 3 of 24. Log base 3 of 24, this is just a number. It's a decimal number. And we can evaluate that with our calculator. We could go to our calculator, hit math, go to log base 3 of 24, and we get 2.89 and some change. Okay, so it's just a number. So what we've done is we've gotten rid of the base of a 3, and we've created a problem where it's only one step away from getting x by itself. We just divide by 5 on both sides, and now I got log base 3 of 24, all divided by, rewrite that, 24, all divided by 5. That's the exact solution. The decimal approximation for that would be take the log base 3 of 24 and then divide that answer by 5. And we're going to go, let's go 3 decimal places, so that'd be 0.579. So we get the exact solution is log base 3 of 24, all divided by 5, or the decimal approximation being 0.579 out of that. So that's the ignoring the bases. We were just kind of hand waving an actual math operation that made that happen. When that number is not nice on the other side, you can't ignore that that operation. You've got to use that log to get there. So let's look at another one like that. This is V. 2 to the 3x plus 1 is equal to 15. Okay. So this one has a nice base of a 2 on the left side. So it's already a prime number there. That's good. I know 15 pretty well. It's 3 times 5. It's not 2 as a number. So I know, hey, I can't do the little trick where I get the bases the same. But I can use a logarithm to solve this. And I can use the log base 2 of both sides. It's legal to do that because I'm doing it to both sides, right? And on the left side, I'm taking advantage of the fact that, hey, that's going to cancel each other out and leave me 3x plus 1 equals log base 2 of 15. And now I'm going to try to get x by itself. So I'm just going to work this. I'm just going to keep in mind that that ugly thing right there is just a number. And I'm going to leave it written like that instead of having to write out the big long decimal for it. So I'm going to leave it as log base 2 of 15. I'm going to subtract 1. So it's going to be 3x is equal to log base 2 of 15 minus 1. And then the last step would be divide by 3. Divide both sides by 3. Log base 2 of 15 minus 1 over 3. And then I'm going to get the decimal approximation for that as well. So this is the exact solution. Or you could write it like this. Log base 2 of 15 over 3 minus 1/3. Both of those ways are exactly the same. You know, they mean the same thing. So the decimal approximation, I'm going to use the calculator to help me with. So I'm going to get log base 2. So math, log base 2 of 15 minus 1 divided by 3. And I'm going 3 decimal places, so 0.969. And I used a logarithm to solve an equation. Again, you're going to use the same base as the exponential had as a base. So here we had a 2 as the base, so we used a log base 2. Up here, we had a 3 as the base, so we used a log base 3. So if it's a 5 as a base, you can use log base 5. Technically, if it's a 27 as a base, you could use a log base 27. It works the same way. Okay. So whatever the base is on the exponential, that's the log base that you need to use to solve. Out of that. All right. Now, last thing in this section, this is still section 6.5. I mean 6.4. I think we're going to get 6.5 tonight, which is fine. No big deal. It is to find the inverse of each function. All right, so this is W. F of x is equal to natural log of x minus 3. And we're going to find the inverse of that function. So we got to kind of go back to what we talked about for inverses in, was it chapter 5 that we did inverse functions? Or was it the first part of chapter 6? Either way, inverses swap x and y. So I know f of x is the same thing as y. And inverses swap those two. So I'm just going to swap where the x and the y are. And to find the inverse, I need to get y by itself again. Okay? So to get y by itself, I've got to undo this logarithm that's here. What's the base of that log? Well, it's one of the common logs. So natural log and then log base 10 are the naturals. So natural log is log base E. So E is the base of that log. So if it helps, because this is not a final answer, maybe you can rewrite it that way. And that will help you remember that that's log base E. And we can undo a log base E by doing the opposite of taking a log. Well, what's the inverse of a logarithm? It's an exponential. Okay. So what we're going to do is we're going to take this base and we're going to, what the mathematical term for it is exponentiate each side with that base. So since this one was log base E or natural log, we're going to make E the base on each side. And that little symbol is the caret symbol. That just means, hey, E's the base. This whole side now is the exponent. And what happens, the reason we want to do that is because these cancel each other out. And it gets rid of the logarithm for us. On the left-hand side, I've got e to the x. On the right-hand side, now all I've got is y minus 3. And that's stinking easy to get y by itself now because we got rid of the log. All I got to do is add 3 to both sides, and I've got y by itself. So plus 3. So that's e to the x plus 3 is equal to y. And that is my inverse. And my function inverse notation, e to the x plus 3. Okay. So the exponentiating is the key to getting rid of that. So whatever the base of the logarithm that's in the problem is, you're going to exponentiate with that base. And that's going to help us later on in the chapter when we go to solve some much more difficult logarithmic equations. So let's look at this one. Let's say we had g of x is equal to log base 4 of x plus 5. Okay. So again, g of x is the same thing as y. So I'm going to, go through the motions here of rewriting that. And then what does an inverse do? It swaps x and y. So I'm going to swap x and y. Okay. So now that puts the y inside of a logarithm, and I've got to get rid of that logarithm so I can get that y back out. So what do I exponentiate with here? 4. So 4 is going to be my base. That cancels out the log. Get 4 to the x is equal to y plus 5. One more step. Subtract the 5. 4 to the x minus 5 is equal to y. Go to the inverse notation, which is g to the negative 1 power, or g inverse of x is equal to 4 to the x minus 5. Really one of the easier things that we've done this evening is doing that. Undoing the logarithm using an exponentiation is what the mathematical term for it. So Let's do one more of those, and then we'll be done. So let's say we had f of x is equal to log of 3x minus 8. And we want to find the inverse of that. So I'm just going to go ahead and skip the step and write it as x log of 3y minus 8. How do I get rid of that log? That's exactly right. It is the understood 10. So I'm going to exponentiate with 10 as my base. Boom. 10 to the x, 3y minus 8. This one's a little more difficult. Got more stuff going on the right-hand side. So what do I do to get y by itself? Add 8. Yeah. Add 8 and divide by 3. 10 to the x plus 8. 3y. Divide everybody by 3. And if you want to do that individually, 10 to the x over 3 plus 8 over 3 is equal to f inverse of x. Or if you wrote it, f inverse of x is equal to 10 to the x plus 8 over 3. That's the same. And because they're inverses of one another, we learned earlier that if I graphed the original function and this new one, that they should cross and reflect across the y equals x line, if you remember that. Or if you did function composition with them, they would equal x if you worked it out. Not too easy to do with the logarithms and the exponentials to do it algebraically, but you should probably be able to see it graphically with that. So that ends up with the things that we were able to get through to this evening. I didn't know that if I would be able to get through the third one. I was being ambitious with that. So